Okay, I will let the students in right now.
Okay.
Hello, everyone. Good morning, afternoon, or evening, depending where you are. Welcome back to another class. Welcome back, Clinton, Benjamin, Marisa, Mr. Lin. Welcome, everyone. Eh, Welcome back to another class. Today's class will be presented to you by Abdulqader. Then after the presentation, we will have a round of questions if any of you want to participate. If you have a question, you can use the hand reaction to raise a question or leave a comment in the chat. So now, without further ado, you can start, Abdulkader.
Right. Thank you, Antonella. All right. So good morning to everyone, or good afternoon. So currently I'm in Milan, in Italy, and it's around 4 p.m. here. So yeah. So nevertheless, thank you for joining us. So my name is Abdulqader bin Sahal, and I'm super excited to be here delivering this talk. So just a quick introduction about me. I'm a chemical engineer and a researcher currently conducting a thesis on different plastic waste recycling pathways, which makes me happy to share some of the knowledge I learned today with the talk titled Towards a Circular Economy with Plastic Waste Recycling. So for today's presentation, we will begin by an introduction, which will highlight the importance and urgency of addressing plastic waste. Then we will dive into the types of plastic waste that are most commonly produced and managed, underscoring the challenges and opportunities they present. In the next section, we will explore the principles of the circular economy and how these principles can be applied specifically to managing plastic waste. Then we will detail various technologies and methods available for recycling plastic waste, including both mechanical and chemical recycling. In the following pathway, we will discuss innovative recycling pathways that convert plastic waste into valuable products like chemicals, fuels, and even energy. Then we will have a quick exercise to test our understanding, and then we will wrap up the session for the Q&A, where I'll be looking forward to any questions that you may have. So without further ado, let's begin. So as we see in the image in the slide, plastic is everywhere. From our packaging our food to manufacturing our cars, plastic versatility and durability have made it indispensable in nearly every industry. Yet, this convenience comes at a cost. The global reliance on plastic has led to significant environmental challenges. Each year, millions of tons of plastic waste accumulate in landfills, oceans, and ecosystems, causing extensive pollution and harm to wildlife. In fact, let us look at some quick plastic waste facts to get an idea of the situation. So each year, the world generates around 400 million tons of plastic waste. The staggering amount underscores the scale of production and consumption that we must manage more sustainably. Looking ahead, it is estimated that the world plastic production will reach around approximately 1.1 billion tons by the year 2050. This projection is a call for action for us to rethink how we produce, use, and recycle plastic materials to prevent the overwhelming waste that comes with it. Despite the high volumes of plastic waste, only about 15% is recycled annually. This low percentage of recycling highlights a significant gap in our waste management systems and points to the immense potential for improvement in recycling infrastructures and technologies. So, why do we need to remove plastic waste? Well, let's explore the different impacts of plastic waste that necessitate urgent and effective management strategies. So first, environmental persistence. So plastics are notorious for their durability, which unfortunately translates into non-biodegradability. Once in the environment, plastics can persist for centuries, leading to long-term pollution of both land and oceans. This persistence disrupts ecosystems and contributes to a global pollution crisis. Second, it can also be a threat to wildlife. So each year, millions of tons of plastic find their way into our oceans and landscapes, posing lethal risks to wildlife. Marine and animals suffer from ingestion and entanglement with plastics introducing toxic substances into the food chain, affecting biodiversity and the ecosystem health. Third, the economic and health impact. So the repercussions of plastic pollution extend to economic and public health domains. So we have to clean up the plastic waste that incurs significant costs and diverse resources that could be used for other resources, so for our community development and so on. Furthermore, plastics release harmful chemicals such as bisphenol A, which is BPA, which contaminate our water and soil, posing potential health risks to humans and animals alike. And lastly, which is very important, the climate change contributor. So perhaps less known is the role of decomposing plastics in climate change. As plastics break down in landfills, they release methane, which is a potent greenhouse gas. This process exacerbates global warming, linking plastic waste management directly to our broader climate change challenge. So understanding these reasons underscores the importance of our efforts in recycling and managing plastic waste, aiming not only to protect our environment, but also to safeguard public health and ensure a sustainable economic future. So in this segment, we will delve into the types of plastic that contribute most to the waste streams and discuss their properties and application. Understanding the characteristics of these materials, such as their durability and resistance to degradation, helps us comprehend why plastic waste persists in the environment for so long. Okay, so before we delve into the specifics of the different types of plastics and the complexities of recycling them, it is essential to understand the concept of so-called plastic waste. So what do we mean when we talk about plastic waste? Well, plastic waste refers to the surplus materials from plastic products that are discarded and not immediately reused. This encompasses a wide range of plastic items that, after serving their initial purpose, become waste products. So this includes single-use plastics, end-of-use plastics, and also production scrap. So single-use plastics are used once and then discarded. So they're the most visible part of plastic waste, often ending up in our oceans and landscape. So for example, this bottle that I have right here is an example of a single-use plastic. So after drinking this, it's going to be discarded. Then we have end-of-life plastics, which are products that have served their intended lifespan, like plastic furniture or technology items, which then become waste. And finally, production scrap are the remnants from the plastic manufacturing process, often overlooked, but is also significant in volume. So let us look at the different sources of plastic waste. So packaging. So packaging is the largest contributor to plastic waste, encompassing a wide range of products from food wrappers to shipping materials. Much of this packaging is designed for single use, leading to a substantial volume of waste that is often not recycled. Then we have consumer products, so everyday items, like I showed you, such as a water bottle, household goods, toys, also contribute significantly to the plastic waste stream. These items typically enter the waste stream where they are no longer needed or when they break. Then we have industrial processes. This source includes offcuts, defective items, and other production-related materials. These are often generated during the manufacturing of plastic goods and can consist of substantial quantities of pre-consumer waste that never reaches the consumer market. Then we have agricultural activities. So in the agricultural sector, plastics are used extensively for purposes such as mulch film and silage wrap. So these plastics are subject to significant wear and tear, presenting unique challenges in terms of disposal due to the contamination with organic material. And finally, which is very relevant, is electronic waste. So we have electronic devices everywhere, and plastics in these electronic devices and appliances represent a growing challenge with the e-waste stream. So as technology rapidly evolves, these plastics contribute to electronic waste, compounding the issue rapidly. So understanding these sources helps us to pinpoint where interventions are most needed and how we can begin to close the loop on plastic waste, moving towards recovery and recycling instead of disposal. So now that we know where our plastic waste comes, let us understand the various types of plastics that contribute to the waste stream. So each type of plastic, due to its unique properties and applications, present different challenges and opportunities for recycling. So there's more than one type of plastic. So let's take a closer look at the most common type of plastics, which are 6 main types. So the first one includes polyethylene terephthalate, or PET in short. So our water bottles are mainly made of PET. Then we have high-density polyethylene. We also have low-density polyethylene. We also have polyvinyl chloride, so PVC. We have polypropylene, PP, and finally, we have polystyrene. So don't worry, we'll be going through every type of plastic in the coming slides to have a better understanding of each one. So let us start first with PET. So this is one of the most prevalent type of plastics known as polyethylene terephthalate. So this plastic type is the cornerstone of the packaging industry due to its incredible versatility and adaptability. So PET is distinguished by its robustness, which makes it an ideal choice for countless applications. So the most recognizable one being the beverage bottles. So beyond bottles, PET attributes are harnessed in a variety of products, including food packaging and textiles like polyester fabrics. So the chemical structure of PET is shown here, which shows that it has excellent barrier properties against gases and moisture. This is crucial for maintaining the quality and freshness of packed goods. So as I mentioned, it is favored for its strength, durability, and lightweight. So when reheated to a molten stage, PET can be stretched, becoming more rigid and slightly opaque as it crystallizes. So let us talk slightly about the manufacturing process of PET. So PET is produced through a chemical reaction known as transesterification, involving two main ingredients, ethylene glycol and terephthalic acid. So here's how it works. So the transesterification reaction is the initial step where the ethylene glycol and the terephthalic acid are combined. The process occurs under specific conditions of high temperature and low pressure, which are critical for facilitating the reaction and forming long polymer chains typical of PET. So as these chains form, they gradually grow into a viscous melt, eventually leading to the production of what we know as PET. So this process is known as the polymerization. Then we have, following the polymerization, the PET melt is extruded through a die to form long strands, which are then rapidly cooled and cut into small pellets. So, for example, like the one you can see on the screen. These pellets are the raw form of PET used by manufacturers to produce everything from the bottles to fibers for clothing, for example. So while PET offers numerous benefits due to its versatility and durability, it also presents significant challenges, particularly when it comes to the impact on the environment and the complexities of recycling. So environmental persistence is an issue because one of the key challenges with PET is the resistance to natural degradation processes. So it is tough to hydrolyze in natural environments, which means that it does not break down easily. So this chemical stability contributes to its persistence as weight, accumulating in our environment for years, if not decades. Another challenge is the recycling challenge. So despite being one of the most recyclable plastics, the recycle of PET is not without difficulties. The chemical stability makes it challenging to recycle. It also requires specific conditions to break down and reformulate, which can complicate the recycling process. Additionally, the wide use of PET in disposable products often mean that it's contaminated with food, beverages, or other materials, which can further complicate the recycling process and reduce the quality of recycled products. All right, now let's move on to the second type, which is polyethylene. So let's discuss polyethylene, commonly referred to as PE, which stands out as one of the most extensively used plastics in the world. So this is because polyethylene is very versatile and can be used in different variations. So let's talk about the chemical structure. So polyethylene is primarily made of long chains of the ethylene monomer, which uses the formula CH2CH2. These chains are the result of the polymerization process that links many ethylene units together, as depicted in the molecular structure shown on the slide. The simplicity of its structure imparts unique properties to polyethylene. It is known for being lightweight yet strong, resistant to moisture and chemicals, and has a wide range of applications from plastic bags and containers and to more robust uses like in the automotive and construction industries. So the versatility of PE can be seen in everyday items such as plastic bags, containers, houseware, like shown in the image. So this extends to both its flexible form in low density variations and more rigid form in high density variations. So what do I mean by the density variation? Well, each type of polyethylene has unique properties and application, making it suitable for different uses in the industry and the consumer product. For example, we have low density polyethylene, which is LDPE. This has a density range of 0.91 to 0.925 grams per cubic meter. LDPE is the most flexible form of polyethylene. It's commonly used in products like plastic bags, containers, and dispensing bottles, where flexibility and durability against tearing are crucial. Then we have linear low-density polyethylene, which is used for stretch wrap, pouches, and plastic wrap. Then we have medium-density polyethylene. This one is used in gas pipes and fittings, sacks, shrink film. Then we have linear medium density polyethylene, which is the same range as MDPE with similar application. And finally, we have HDPE, which is the high density polyethylene. So this is used in high strength applications like milk jugs, detergent bottles, and piping. So for example, in the bottle that I have, this tap, if you look at the instructions here, you can see that the tap is made of HDPE, while the bottle is made of PET. So this is how an example of an application of HDPE. So in our beverage bottles. All right, so you might be wondering on how do we actually classify the different types of polyethylene based on density? Well, the density measurement is done using specialized techniques, which are pivotal in classifying its type. So two common methods include the density gradient columns and the hydrostatic techniques. So these methods allow us to accurately gauge the density, which directly correlates with its strength, flexibility, and suitability of polyethylene for various applications. So another critical factor is the crystalline content of polyethylene. So crystallinity refers to the degree to which the polymer chains are tightly packed together in an ordinary structure. So this arrangement significantly affects the material properties such as the rigidity and the barrier properties. So generally, high crystallinity means increased rigidity and better barrier qualities, making the polymer more suitable for certain uses like rigid containers and high-strength films. All right. Now, let's turn our attention to polyvinyl chloride, commonly known as PVC. So PVC is unique due to its robustness and application where strength and durability are demanded. So it is naturally white and very brittle in its pure form, which makes it somewhat limited in flexibility without the addition of plasticizers. So due to its chemical structure shown here, PVC is used in building and construction for products like pipes and window frames, as well as healthcare applications where its ability to block contamination is valued. In its most flexible form, after modification, it is used for wiring insulation, flooring, and medical devices. So the PVC molecule consists of a carbon backbone with chlorine atoms attached, represented by the chemical formula here, so C2H3Cl. The chlorine content gives PVC excellent fire retardant properties, but also raises environmental concerns during the manufacture and disposal due to the potential releases of dioxins. So there's usually two types or forms PVC is made in. So we have rigid PVC, which is unplasticized PVC, also known as UPVC. So this form of PVC is known for its strength and durability, making it an ideal choice for construction and industrial applications. So rigid PVC is commonly used in the construction industry for pipes in plumbing, sewage systems, and various agricultural applications. So its rigidity makes it suitable for environments that require a durable material that can withstand tough conditions without deforming. Then we have flexible PVC. So by adding plasticizers to PVC, it becomes flexible and can be used in a completely different set of applications compared to the rigid one. So this flexibility is essential for products like the electric cable insulation, flooring, and the medical devices. So flexible PVC is very useful for these different applications. And you can see from the slide, I have two pictures here. So the first one shows an example of the rigid PVC, while the second example is of the flexible one. All right. So generally, PVC is valued for its versatility, chemical resistance, and excellent cost-performance ratio. So modifications and additives can significantly alter PVC's physical properties to suit specific applications. For example, here we have three different variations of PVC shown in the slide. So we have CPVC, which is the chlorinated polyvinyl chloride. This is produced by the chlorination of PVC resin. CPVC features enhanced chemical stability, high temperature tolerance, and flame retardancy, making it ideal for industrial applications, including the hot and cold water pipes. Then we have PVCO, which is the molecular-oriented PVC. So this features a layered biaxially oriented structure that enhances strength and durability. It is commonly used in pressure pipes and highly stressed applications. So applications which require very strong pipe, this would be commonly used. And then we have PVCM, which is modified PVC. This is an alloy of PVC with modifying agents to improve toughness and impact resistance. So it's suitable for high demand applications such as heavy duty hoses and shock absorbers. So we can see how we can modify PVC to achieve certain applications and needs. Now we move on to another type of plastic, which is polypropylene, often abbreviated as PP. So polypropylene is derived from the polyprene monomer, represented chemically as C3H6, making it one of the simplest yet most adaptable forms of alkenes used in plastic production. So it's known for its exceptional chemical resistance, durability, and elasticity. So propylene is widely used across various industries. So this plastic resilience against chemical solvent, bases, and acids makes it ideal for containers and packaging, so such as the food storage containers displayed here, which benefit from its barrier properties and structural integrity. So PP can be categorized into two types. So the low molecular weight amorphous polypropylene. So this type has limited commercial use due to its amorphous structure, and it's typically produced through free radical and cationic polymerization methods. Its applications are specialized, often tailored to specific industry needs, where high clarity and flexibility are less critical. Then we have industrial polypropylene, which is the more commonly used type of polypropylene. It is produced under controlled condition using a transition metal catalyst along with a metal alkyl co-catalyst. So this method enhances the polymer strength and thermal stability, making it suitable for a wide range of applications from automotive to household goods. So let's do some comparison and talk about the properties. So although PP is slightly more expensive than PE, which is polyethylene, it compensates for this with superior properties. So this includes a higher melting temperature, which allows for a wider range of applications and greater tensile strength, making it more robust for various industrial uses. Then we have thermoplastic qualities from PP, which is characterized by its excellent chemical resistance and rigidity. So this means that not only can maintain its form under stress, but it can also be easily melted down and reshaped through recycling process without significant degradation of its intrinsic properties. So let us talk slightly about the manufacturing and application of polypropylene. So it is done in three main fabrication techniques. So the first one is injection molding. So this method is crucial for creating complex shapes with high precision and is commonly used for automotive components, household goods, and medical devices. So the first image as shown on the left. Then we have fiber extrusion, which is used to produce fibers, which are then transformed into a multitude of textile applications from long-lasting automotive fabrics to reusable shopping bags. And then lastly, we have film extrusion, which this technique produces thin, flexible films used extensively in packaging, labeling, and protective covering. So an example of this labeling is also, if I see here, so this labeling is also polypropylene, and this is an example of how film extrusion can be used to make a label of this kind. All right. So let's move on to the final one in the family, which is polystyrene. So this material is versatile also on a transparent thermoplastic. So it's appreciated for its use in both solid and foam states. So it's known from its wide application range, so from consumer packaging and insulation materials. So for example, when we buy a new TV, usually we will have a polystyrene foam that comes to protect that TV in the box. So this is an example of a polystyrene application. So like the other plastics, polystyrene also comes in different forms. So first we have polystyrene form, which includes extruded polystyrene, so EPS, and expanded polystyrene, XPS. So the EPS is lightweight, commonly used in packaging such as packaging peanuts and disposable coffee cups. XPS on the other hand is a denser foam often used in building models and insulation. Then we have regular polystyrene plastic, frequently used in disposable cutlery and laboratory wear. Then we have polystyrene film, which is utilized in packaging through vacuum forming. So films can be made into oriented polystyrene for applications requiring rigid but an inexpensive material. So just a quick brief about the manufacturing process of polystyrene. So it involves two key processes, so fractional distillation and polymerization, like other plastics. So the initial stage is crucial, where polystyrene production starts with the distillation of hydrocarbon fuels to isolate styrene monomers using a catalyst to enhance the reaction. Then this process forms the basic building blocks of polystyrene. Then we go to free radical polymerization, where once we have the styrene monomer, it undergoes polymerization. So this occurs at a controlled temperature of about 102 degrees Celsius, using free radical initiators. So this method is pivotal in linking monomers together to form long chains of polystyrene, resulting in a polymer with high molecular weight. So the process doesn't end after polymerization. To ensure the purity of the final product, the unreacted monomer and any dilutants are removed under vacuum. So this step is essential to maintain the quality and characteristics of polystyrene produced, ensuring it meets the industry standards for various applications from packaging to building and insulation, so on. So we have 6 main types of plastics. However, it is not limited to only these 6. We have another category labeled as other, if you have seen sometimes. So this category encompasses a variety of plastics that do not fit neatly into the standard classifications. So these materials may vary widely in their chemical composition and properties, including their recyclability and biodegradability. So examples include polycarbonates, polylactic acid, and acronyl butadiene also known as ABS. So let's just talk quickly about each example. So polycarbonates or PC represents a significant segment with the others category. So it's known for its unique properties. So this PC type of plastic is typically used for eyewear, protective gear, and bulletproof glass. However, despite these advantages, polycarbonates have raised health concerns due to the release of bisphenol A, so PPA, so especially when used in food containers and baby bottles. So as a result, the industry is exploring PPA-free alternatives to maintain the functionality of polycarbonates without the associated health risks. Then we have polylactic acid. So this biodegradable plastic stands out because it's derived from renewable resources such as cornstarch and sugarcane, aligning with the Sustainable Development Goals. So the two key properties is that it has low melting point and it's insoluble in water. But the most benefit, in my opinion, is that it's environmental friendliness. So it's biodegradable, which means that it can break down into natural elements under the right composting conditions. So unlike the traditional plastics, which persist and stay in the environment. So a famous application of this type of plastic is 3D printing applications. So its low melting point and biodegradability make it a popular choice for home and professional 3D printing projects, providing a more sustainable alternative to petroleum-based products. Then we have the final type, which is ABS. So ABS is renowned for its high impact resistance and strength, which is essential for products that require longevity and reliability. It also has good shock absorbency, which makes it an ideal choice for protective gear and also toys, for example. So a popular example of ABS is Lego. So as you can see in the image, these building blocks are actually made from ABS. So this is a common example of this type of plastic. All right, so enough talking about the plastics and the different types. I hope you have a good idea of what the plastics are, but now let's take a closer look at the distribution of the plastic waste demand actually. For example, this data is from Europe. So all right. So if we see this pie chart, we can see that polypropylene makes up the largest portion at 20%. So this is widely used because it's a very versatile and durable plastic. Then we have low density and linear low density polyethylene come next, accounting for 17%. Then we have high density and medium density polyethylene, making up 13%. And then we have PVC around 10%, and polyurethane and polystyrene around 8%, 7%. So we can see that mostly polyethylene and polypropylene are used a lot based on this data. But how about the plastic waste composition? So usually we know that the production is something else and the waste is something else. So when we get a plastic waste stream, what do we expect from this plastic waste? Well, based on this European patent, it said that plastic waste composition consists around 50 to 60% of polyethylene, 20 to 30% of polypropylene, 5 to 10% of polystyrene, and then 1 to 10% of other types of plastic. So we can see that the polyethylene and polypropylene are also very prevalent in plastic waste, which will be impacting on how we recycle the plastic. So this is important to know. So we've seen that the demand for these plastics is quite high, which makes sense to why we have a significant amount in the plastic waste composition. All right, so let us shift now We already know more about plastics so far and their uses and different types. It's more important now to shift to a core concept that we'll be talking about today, which is circular economy. So some of you might already have heard of this term, but others may wonder, what is it and why is it important? Before we dive into the benefits of the circular economy, it's crucial to understand the traditional model that most of the world operates under, which is the linear economy. So the linear economy is based on the take, make, dispose model. So this approach starts with the extraction of resources, followed by the transformation into products, which are then consumed and ultimately discarded as waste. So this process is categorized by a one-way flow of materials. But what are the key features of linear economy? So resource extraction, manufacture and consumption, and waste creation. So this has a lot of impact on the environment and the economy. So this promotes unsustainable resource use, economic inefficiency, and inadequate waste management. So understanding the linear economy highlights why transitioning to a circular economy or a circular approach is essential for sustainable development. So after understanding these limitations, let's explore a transformative approach, which is the circular economy. So the circular economy is a regenerative system in which resource input, waste, emission, and energy leakage are minimized by slowing, closing, and narrowing the material and energy loops. So this can be achieved through long-lasting design, maintenance, repair, reuse, remanufacturing, refurbishing, and recycling. So transitioning to a circular economy requires a fundamental shift in our approach to production and consumption. It is built on three core principles that guide this transformative path. So first, design out waste. So the circular economy begins with design. Products are crafted for longevity, recyclability, and reusability, minimizing the waste at every stage. So this principle challenges manufacturers and designers to innovate in ways that preserve resources and extend the life cycle of products. Then we need to keep products and materials in use. So we need to emphasize repairing, refurbishing, and recycling to extend the life cycle of products and materials. And finally, regenerate natural systems. So encourage practices that restore and rejuvenate the environment, such as using renewable energy and returning valuable nutrients back to the soil, for example. So the circular economy offers substantial economic and environmental benefits that propel us towards a sustainable future. So first of all, we have resource efficiency. So it reduces the need for new resources by maximizing the use of existing materials. We also reduce waste by converting products into new resources and recovering materials at the end of product life cycles. Also, it promotes innovation and growth, where it stimulates innovation in business models, materials, and product design, contributing to economic growth and job creation. But how about a circular economy in plastic waste, which is the kind of the focal point of today's talk? So we can work on 2 points, design innovation and reducing single-use practice. So to make plastics that are, first, must ask manufacturers to make plastics that are easier to recycle or that can break down more easily in the environment. So this means making plastic that lasts longer and can be used again instead of throwing them away after one use. So for example, plastics like PLA that we have just mentioned. Then we also need to reduce single-use plastic. So we need to decrease our single use as individuals. So like plastic bags and straws, we need to find reusable options such as perhaps a metal straw or a metal bottle instead of plastic bottle, so we can use less plastic and make less trash. And then we can also improve two important aspects, which is the recycling infrastructure and also develop new chemical recycling technologies. So we need to invest in new technologies and facilities to enhance the recycling process and handle more complex plastic materials. And we need to develop chemical processes to break down plastics into fundamental components for reuse in new products. So we know that plastic waste is crucial now for a circular economy. So let us discover the different type of plastic waste recycling techniques. So plastic waste recycling is categorized mainly into 4 types. So we have primary recycle, which is the ideal scenario where we take a used plastic bottle and recycle it directly into a new bottle. This process is often known as closed loop recycling, showing that the quality of the material is reserved. It's the most sustainable form of recycling. However, it's not really possible because after some times the material and the plastic would degrade and you cannot continue with this primary recycling anymore. This is where we have secondary recycling, which is also known as mechanical recycling. So this method involves breaking down plastics into smaller pieces. These pieces are then used to make new products which may be different from their original form. While this method does not keep the plastic within the same product cycle, it still keeps them out of the landfills and uses them in other forms. Then we have tertiary recycling, which is which chemical recycling is a common example. So this method breaks down plastic into basic chemicals. Then the derived material can be used to make new plastics or other products, extending the life cycle of initial materials, even if they're not used in the original form. Then we have currently recycling, which is direct incineration, basically. So this is energy recovery. So this process involves converting plastics that cannot be recycled conventionally into energy. This is used as the last resort, as it involves burning plastic, which can have some environmental consequences. However, it does provide a way to extract value from waste that would be just discarded regardless. So this is a more, I guess, detailed or complicated flow diagram of different plastic waste recycling categories. However, I just want to bring your attention to mechanical and chemical, and the final one, which is direct incineration, which we'll be talking about today. So mechanical recycling. So let's talk about mechanical recycling. So this method involves physically reprocessing waste plastics by sorting, shredding, and remelting them into new products. The key point here is that the basic chemical structure of the plastic is not changed, which is why it's given mechanical recycling name. However, in contrast, for chemical recycling, it breaks down plastics down to their chemical components. So these raw materials can be either repolymerized to new plastics or used as base materials in other chemical products. This method allows us to recycle more contaminated or mixed plastic streams that mechanical recycling cannot process effectively. So let us now talk about mechanical recycling in detail. So mechanical recycling transforms washed and dried plates of single polymer streams into new products through physical processes that maintain the material's original structure. So it is suitable for monostreams that consist at least 90% of a single polymer. So we know that there's different types of plastic, and the plastic waste consists of a different composition. So mechanical recycling is only suitable for like single stream. So a single stream of polypropylene, a single stream of polystyrene, and so on. So purity thresholds are subject to industry debate, but standards vary around 90 to 95%. Then post-granulation, recycled polymers are frequently blended with a virgin resin or additives to enhance their performance. And the products range from 100% recycled content to those fraction of blended recyclate, commonly target at 30% blend due to the policies. So usually the product from mechanical recycling can be blended with virgin plastic to improve its quality. So mechanical recycling is noted for its high yield, so of 95% with low energy demand investment. The result, the resin often has lower technical quality compared to the fresh or the virgin resin due to the mixture of polymer grades, some degradation, and potential contamination with foreign materials. However, the majority of recycled plastics are directed to non-food contact applications, with exceptions like the PET bottles. Then we have solvent-based mechanical recycling. So this method plays a critical role in recycling a more challenging contaminated plastic waste stream. So solvent-based mechanical is basically a process to extract pure polymers from contaminated waste streams. This process involves using solvents to swell polymers, helping to release and remove low molecular contaminants like dyes and plasticizers. Alternatively, it can selectively dissolve and then reciprocate polymers, which is particularly effective for separating components in materials like multi-layer films, for example. So choosing the right solvent is important, as the effectiveness of the recycling method heavily depends on the choice of the solvent, and also the energy efficiency heavily relies on the recovery and the purification of the solvent used in the recycling process. So let's talk about the steps briefly. So the first step is involving dissolving the polymer. Then the second step would involve the reprecipitation. So after dissolving, an anti-solvent, for example, like cyclohexane, will be added. This causes the polymer to precipitate out of the solution, separating it from the contaminants and from the solvent mixture. Then we have separation and drying, where it goes filtration and drying. And it's important to note that solvent energy recovery is energy intensive, requiring approximately around 50 to 100 millijoules per kg, depending on the specific procedures and materials. So despite the energy input, this achieves a 95% recovery rate of the targeted polymer, ensuring minimal loss. So just a quick comparison between solvent-based mechanical recycling and conventional mechanical recycling. We can see here from the advantages and disadvantages that solvent-based mechanical recycling is good. However, it is relatively high technical requirements and relatively high cost, whereas mechanical recycling is much cheaper, but of course, it comes with its own limitations. So in Europe, an average of 10% of plastics are mechanically recycled. So what happens to the rest, or why only 10%? Well, this is because mechanical recycling requires plastics to be sort of pure and free from contaminants to be effectively recycled. So this restricts the application to a narrow range of plastic waste, leaving out many commonly used plastics. So to enhance our recycling capacity and address the diverse nature of plastic waste, we need to develop and implement additional recycling methods. So these include chemical recycling, which can handle more complex and contaminated plastics by breaking them down into their basic components for reuse. So one of the promising advancements in chemical recycling is solvent-based depolymerization. So it's a specialized method to reclaim and repurpose materials from used plastics. So what is this process briefly? So this process breaks down plastics, for example, like PET, back to the original monomers. So this is achieved through solvolysis processes, including hydrolysis, alcoholysis, and aminolysis. So these are different chemical processes that break down the original plastic to its monomer, where the monomer can be used again to build and repolymerize to different plastics. So usually the separated monomers are nearly as pure as virgin materials, thanks to the sophisticated purification techniques such as distillation or crystallization. This high purity is crucial for the monomers to be suitable for high-grade applications like new food-grade containers. So these are some examples, reaction examples of solvent depolymerization. So it might be too complex, but let me just give an example, for example, about the third one, which is glycolysis. So glycolysis breaks down the PET using ethylene glycol to recover this molecule, which is BHET. So this is a reusable monomer which can be used to make different plastic products. So this is an example of how we can break down the solvent to obtain the monomers to make those plastics. Then we move on to pyrolysis. So pyrolysis involves heating plastic waste to temperatures between 400 to 800 degrees Celsius in an oxygen-free environment. So this process avoids burning the material and instead breaks it down chemically. So it's a sort of thermal cracking. So the output from the pyrolysis typically contains 75% of olefin-rich oil or wax, which is a valuable resource for creating new plastic material or further refinement. Then we have 10% gases, and then we have 15% char or tar, which is the black carbon material. So the lighter outer fractions can be further cracked into olefins and aromatics with a yield of 70%, typically by co-processing in a naphtha cracker. So let us take a look at what a pyrolysis reactor would look like. So we take the plastic waste, we enter it in the pyrolysis reactor, then we supply a lot of heat, and from that we break down the plastic waste to three components of pyrogas, pyrolysis oil, and char. Usually the pyrogas can be used to recover some energy by using it to run steam turbines, for example, and the pyrolysis oil can be used as a product. And typically the char does not have a lot of value, so it would be discarded. All right, so pyrolysis and subsequent steam cracking are endothermic, which means that they're powered by the combustion of hydrocarbon gases produced during the process. So with minimal external energy input beyond electricity for the compressors. So this gives around 6.6 millijoules per kg. And the aromatics are of virgin-like quality, which is suitable for conversion into high-purity polymers for certain applications. So just an example of how we can use plastic waste to fuel through pyrolysis and a circular economy approach. So we produce plastic, we collect it as waste, do pyrolysis. This helps to give us monomer formation, which can be used to make products and also can be used to repolymerize to make further plastics. Now we move on to another technique, which is gasification. So gasification is a process that transforms mixed and contaminated plastic waste into syngas, a mixture of carbon monoxide and hydrogen. So it operates at high temperatures, about 1000 degrees Celsius, through partial oxidation with oxygen and steam, utilizing internal heat generated by burning a portion of the hydrogen produced. So the syngas is then processed through a water gas shift reaction to adjust the hydrogen to carbon monoxide ratio. So at the bottom is the reaction which produces syngas, so CO2 plus H2. So this is a process scheme of the gasification chamber. So this is how it typically looks like, where we have plastic waste mix that is fed into this chamber, and then high pressure steam along with controlled amount of oxygen is also injected at the chamber. So here at the top. So this oxygen is crucial for partially oxidizing the plastic, while the steam acts as a source of heat and facilitates the gasification reaction. So under those conditions, the plastic waste undergoes a serial of thermal decomposition, and after the reactions happen, we obtain syngas. After we obtain the syngas, we usually do syngas cleaning through a scrubber, which is passing through here. This is basically to purify the syngas and ensure it's of high quality. And then we also have byproducts like tar and coke that are generated, which are typically removed at the bottom of the gasification chamber and disposed according to environmental regulations. And lastly, the water used in the scrubber also contains contaminants. So this is wastewater, and it is sent respectively to the wastewater plant. So we've seen the chemical recycling technology. Let us discover some possible interesting pathways to the technologies we have discussed so far. So we talk about plastic to energy. So the conversion of plastic into energy is a very important pathway and is actually practiced a lot. So this is commonly done through incineration, which stands as the common approach in this domain, where we completely burn plastic waste at a high temperature, around 1000 degrees Celsius. So this process isn't about disposable, it's about powerful way to burn this plastic waste to recover energy. So by burning this plastic waste, we get a lot of heat, and this heat is utilized to produce steam, which in turn drives turbines. So these turbines are a heart of the electricity generation. So to show you what I mean by this is a simplified scheme where we will put the plastic waste into incinerator. We're going to burn this plastic waste. This plastic waste will provide heat when it's burned, and heat will be used to produce steam. Then the steam will be used to power the steam turbines. So the electricity that generated from this turbine, some of it will be sent to the grid, and some of it will be used to self-sustain the plant. So we are not using external energy. So we can just use the energy that is produced from the turbines, and any excess energy can be sent to the grid, which is then sent to our homes, for example. However, this process of burning creates some amount of CO2, and now common plants, they would do is that they would capture the CO2 and use it somewhere. So in this case, we are not, environmentally polluting, and we are actually making full use of our products in this plant. Another pathway is plastic to methanol, which is interesting. So this process happens thanks to gasification that we've just talked about. So this process begins with the gasification of plastic waste, where plastic waste are converted into syngas, so carbon monoxide and hydrogen. Then the water gas shift reaction is the next step, where the syngas composition is adjusted using this reaction to increase the hydrogen content, optimizing the ratio for methanol synthesis. And then finally, we have methanol synthesis, where the syngas is catalytically converted into methanol through a process known as methanol synthesis. So what is this methanol synthesis process? Well, it typically occurs in a shell and tube reactor design at temperature ranging from 200 to 300 degrees Celsius, around 50 to 100 bar. Then a copper-based catalyst is used, and the reaction is shown on the bottom. So we have syngas, which is catalytically converted to methanol. So this is a simplified plastic to methanol block diagram. So we have plastic gasification, light hydrocarbon treatments, syngas conditioning, then we have methanol synthesis, and then methanol distillation, so to purify our methanol. However, the actual process is very complicated. As you can see here, this is a more detailed block diagram, but just to give you an idea of how the process goes. All right. So I see we have around 15 minutes. I'll try to go ahead fast so we can have more time for the Q&A. All right, so we have another pathway, with the last pathway is plastic to hydrogen pathway. So this converting plastic waste to hydrogen involves breaking down the materials through pyrolysis. So we've seen that technology. It consists of 3 stages. So pyrolysis, steam methane reforming, and water gas shift reaction. It can also involve a neutralization stage if there is PVC in the plastic waste, since it produces hydrogen HCl, which is hydrochloric acid, which needs to be removed from the product streams. So steam methane reforming is the next step after pyrolysis, which is used. And then after steam methane reforming, we have the water gas shift reaction. So simultaneously or sequentially in the same reactor, the water gas shift reaction converts the carbon dioxide, the carbon monoxide, and more steam, which is water, into additional hydrogen and carbon dioxide. So this maximizes the hydrogen output and efficiency. And then we have neutralization in the presence of PVC. So sodium hydroxide can be used to neutralize that hydrochloric acid, forming water and sodium chloride, which is removed later in the stages. All right. Okay. So a study simulated by GE investigated and the feasibility of production of hydrogen from plastic waste in countries like Malaysia, Indonesia, and Brunei. So they used 20,000 kilograms per hour of mixed plastics, so PE, PP, PET, PS, and PVC, which resulted in the production of 340,000 tons of hydrogen per year. So their economic analysis actually pointed to annual profits estimated between 271,000 to around 360 actually million, not thousand. So this shows that plastic to hydrogen is actually a promising pathway which could be considered in the coming future, especially when the renewable technology becomes even further improved, which can be used to power these plants. All right, so just to ensure that everyone is on the same page, we can have a quick exercise of basic MCQ questions. So the first question is, which type of plastic waste is commonly used for beverage bottles? So feel free to raise your hand and talk in the mic of what you think the answer is. Don't be shy. Feel free to voice out your opinion.
Yeah, if they're comfortable.
All right, so maybe I can all right, Clinton, feel free to we cannot hear you. I think you're muted. All right.
I'm just trying.
No, feel free,
Probably
try. Yeah.
the polyclinic for the late, it's PET.
Yes, yes, you're correct. So the answer is polyethylene. So, for example, this bottle that I'm using is mainly made of PET. And thank you, Clinton. All right, so let's move on to the second question. What does the circular economy emphasize? So does it emphasize the use of single-use plastics, minimizing waste and maximum resource use, increasing production rates, or the use of non-renewable resources? I think Cheche, you have raised your hand. Feel free to voice out your answer or what you think the answer could be.
Oh, the B.
Yes, perfect. Yeah, so circular economy emphasizes minimizing waste and maximizing resource use. All right, third question. So which process is not involved in mechanical recycling? So is it A, use of virgin resins, B, pyrolysis, C, granulation of plastic waste, and D, purity sorting of plastic streams? So anyone would like to answer, feel free to open your mic. Yes, go ahead, Owe, if not mistaken. Yeah.
D.
B, yes, correct. So pyrolysis. So pyrolysis is not a mechanical recycling technique, rather it's a chemical recycling technique. So we just have two more. So which recycling process involves breaking down plastics into their chemical components? So yeah, so this one would be chemical recycling. So we've just mentioned an example, which is pyrolysis. And finally, let's go on to the last question, which, what is the main challenge with incineration of plastic waste? So who would like to answer this final one? What about Antonella? Do you think you'd like to attempt to answer this one? Okay, go ahead, Owa. Go ahead.
A.
All right. So you mentioned A again?
Yeah.
Okay, so it's not A actually, it is C because incineration we recover energy from it, but the challenge is that we could produce carbon dioxide by when we burn this a lot amount of plastic waste. So of course we need to ensure to control that by either utilizing that CO2 or carefully capturing it. Hernandez, thank you for your contribution. All right, with that, I'll just try to end with some statistics. So these are the global and European plastic waste management stats. So we can see that in Europe, we have more recycling, so around 43% compared to the global. So globally, we have 40% of landfills of plastic waste that just end up in the landfill, 16% is recycled, and 25% is used for energy recovery, so which is burned. But in Europe, currently we have 25% that is in the landfill, 32% that is recovered, and 43% is recycled. However, we can see that there's still much room for improvement, and this is why we should integrate different recycling pathways. So we should collect the waste, and then some of it we can send to mechanical recycling, some to solvent-based mechanical recycling, some to chemical depolymerization, some we can send to pyrolysis, and some for gasification. So this is how we can integrate more than one way or more than one plastic pathway to help improve the use of plastic waste and not just send it to the landfill. So the benefits of the circular economy in the plastic industry, so we'll have increased recycling rates, we will decrease the use of natural resources, we will reduce the CO2 emissions, we will have controlled exports, and finally, with that, we will have stable markets. So this brings me to the end of my presentation. Here are some of the references that I've used. So now we move on to the Q&A session where, yeah, you can let me know any questions that you have about the presentation, or even if it's outside the scope of the presentation, no worries. So please feel free to raise your hand if you'd like to ask something.
Question, reaction, or leave a comment in the chat. We have a question from Clinton. Let's see what he has to say.
Hi, good evening, comrades. I just needed to understand which type of greenhouse gases does burning plastic stain in the airspace? Because if you have 4 greenhouse gases, so when I burn the plastic, what type of greenhouse gases does it go to? Is it methane? Is it carbon dioxide? It's my question.
Okay, very good question. All right, so when we work with incineration, which is burning the plastic, so we aim for complete combustion. And when we do complete combustion, then CO2 will be the main gas that we need to take care of. So to answer your question, that will be CO2, and this CO2 better will be, captured. So example, CO2 will be the main gas or the main greenhouse gas that we need to focus on using, and this CO2 is, of course, a main contributor to global warming. So yeah, I hope that answers your question.
Do anyone else have a question? We can answer. Cici Jules has a question. Let's see what they have to say.
Thank you very much. So it was a very good presentation. Just to remind me how, if it is possible to process from plastification and reach to the gasification stage. Is it possible, or vice versa?
Sorry, could you repeat the question? You meant from
I say I want to
gasification
know
soil?
if you can. I want to know if from the plastic you can get the gas, or vice versa.
Yes, of course. So this is what gasification is actually doing. So in gasification, so yeah, so in gasification, we take plastic waste and we basically heated with oxygen and steam, and this produces syngas. So syngas is basically a mixture of CO2 and hydrogen. So this syngas is a very important component that's used in the chemical industry, for example, like to make methanol, like I mentioned previously. So we take plastic waste, we put it in the gasifier or the gasification chamber, and we obtain gas. And even with pyrolysis, which is another way, we obtain pyrogas, so gas, oil, and some tar. So of course, when we burn plastic waste, there's always going to be a gas product, and it differs from technology to technology. But the most useful gas that we can obtain is syngas, which is a combination of carbon monoxide and hydrogen. And this can be used to produce methanol and different chemicals in the chemical industry. Yeah, I hope
Okay.
that answers your question.
Yeah, thank you. Thank you. Yeah.
Yeah, you're welcome.
We can answer one more question since we ran out of time. So let's see what Zakaria has to say.
Yeah, thank you very much. A very robust and very important topic, actually. Thank you very much for the exposure that you have given us. My question is, which recycling or recycling type suitable for countries like underdeveloping countries like Africa, Asia, in terms of cost and simplicity or technology transferability?
All right, very good question. So actually, I have seen a recent video that there's in Ethiopia, there's a plastic waste to energy plant that is actually running right now. So this is the fourth type of pathway, which is burning the plastic to recover energy. So I think this type of technology is not very difficult because it's already been practiced. However, the important part is in this plant in Ethiopia, they use the CO2 that is released from the plant, and they use it to make another type of product. So the CO2 is important precursor in different chemical products, and they use that and utilize it to actually make products. So I would say plastic waste to energy would be the most feasible one, because other technologies like pyrolysis and gasification are still under technological development, and I believe they're not very, ready to be implemented everywhere. Yeah.
And you mean that the CO2 is captured, it's not going to
Yeah.
the air?
Yeah, if perhaps if I can leave the link, I'll leave the link of the LinkedIn video of that Ethiopian waste energy plant. There's a very nice video that explains how it works. So perhaps I can share it right now in the Zoom chat, so you can go ahead and see how it works actually. Yeah.
Thank you so much.
Yeah.
Thank you so much.
You're welcome.
Thank you, Abdulqader. Thank you, everyone, for being here today. Remember that every day at the same hour we have a class. So see you next week. Bye-bye.
All right. Before we end, could we take perhaps a group photo, all of us? Okay, wait. So whoever has his camera open, we can have a group photo.
I think it will be better if you stop sharing and you can take the photo.
Sure, yeah. Okay. All right, let me stop sharing.